let's move to the next presenter. The next presenter is, let's open the Professor Peter Wust. You have here the presentation. He is from Berlin. He is an oncologist radiotherapist, and his topic is about a biophysical framework to analyze preclinical data on non-thermal effects. I think a very, very important topic. So good morning, Professor Wust. Are you hearing me?
Do you see me? No.
Can you see the presentation?
Yes.
Ah, okay, because we cannot see it.
Okay.
We cannot see the presentation at the moment. Genau.
Sie hatten die doch vorhin so schön.
Yeah, diese.
Please share the presentation because you are not sharing the screen.
No.
Yes, now sharing. Okay.
Okay. Thank you very much for the invitation and for the good or splendid or excellent organization of the Congress. I want to present, or we want to present, some ideas to understand and classify membrane effects of electromagnetic fields, to understand better why modulated electro-hyperthermia can work as a monotherapy, as we have seen already in a very interesting clinical study. Moment. So we have already evidence that anti-proliferative effects on cells are induced by sinusoidal radiofrequency and enhanced by additional amplitude modulation. So the best known technique is, of course, MEHT, which we are dealing today, or Oncothermia as it also called. So it works at 13 megahertz and the amplitude modulation is at 100 hertz with a ping noise decrease. And the SAR, the specific absorption rate, is quite low for clinical application in the range of 10 to 20 watt per kilogram. But there is another interesting technique already in use. This is Terabionic, which works at 27 megahertz, and there are tumor-specific modulation frequencies in the range of hertz to 10 kilohertz, and the SAR is even lower, is in the range of, is less than 2 watt per kilogram. And there is a third interesting technique. This is the tumor treating field technique, which has already been validated by a clinical study. This works at a frequency of some 100 kilohertz, but the SAR again is quite low. It's in the range of 5 to 10 watt per kilogram, and obviously there is, for all three modalities, no very large temperature increase. So the temperature might be in the range of 38 to 39 degrees centigrade, but it is much far away from the temperatures which are required for conventional hyperthermia, which is a typically application of hyperthermia. So for all three techniques I have here listed, recently preclinical and clinical studies are available. And there are very first studies already for application of amplitude modulated radiofrequency, and it started in 98, in the 80s. And we can say that observations of such effects go back to the 80s and were repeatedly published. However, it remained until now, the existence of non-thermal effects remained until today a minority opinion. For all techniques we have spoken about, also Oncothermia, Terabionic, and TTF, increase of intracellular calcium is documented. And there were already specific low voltage gated or high voltage gated calcium channels identified by preclinical investigations. Therefore, we investigated the educated guess that membrane effects of electromagnetic fields are causal for that, what we see clinically and preclinically. Then SAR or E-field amplitude are decisive parameters, but temperature is still not the most relevant parameter, but a covariable, but might be lower than for conventional hyperthermia. So in our study, we have just published in scientific reports, we use the preclinical device of Oncotherm, the lab EHY200, and this is basically a series circuit. And here you see between the electrodes, you can calculate E-field amplitude, and it is it is basically a resonance circuit with a defined E-field between the electrodes in the specimen, which is green here, and it works under resonance conditions. So you have a specified E-field here, but you have to know the SAR or the E-field in the specimen. And so our suggestion is to measure the SAR in the specimen via temperature gradient over time after power on. And you see in our case, this is a typical temperature time curve in the specimen. We have a low SAR in our publication in the range of 35 watt per kilogram, which is not very high. Our first model deals with the effects of radiofrequency at ion channels. This is an ion channel. Ion channels act like diodes with forward direction along the electrochemical potential. So in case of a potassium channel, which is shown here, the electrochemical potential is going from intracellular to extracellular. So this is a forward direction of the diode, and there is a half wave rectification in caused or by this diode, and a low pass filtering caused by the resistance of the ion channel and the capacitance of the membrane. And so finally, a DC voltage in the range of 1 microvolt is generated along the channel and along the forward direction of the channel. And in case of the calcium channel, which is probably the major cause of the calcium increase and of the non-thermal effects. So the calcium channel looks very similar to all the other channels. So we have a special model of this channel, which is representative for all other ion channels. And in this case, the electrochemical potential is going from extracellular to intracellular. And if the channel opens, there is a strong influx of calcium from outside into the cell. And as you know, the calcium concentration inside the cell is in the range of 100 nanomole per liter, and this is of course a very small concentration, and the concentration gradient is 10,000 to 1. But there is also a gate, of course, for every channel, and this gate must be open that the ions go out or in along the channel. We have calculated ion fluxes, assuming 1,000 open ion channels for 1,000 seconds, which might be a realistic assumption for a cell. And we see that for all ions, relevant ion disequilibrium or imbalances can occur, but especially for calcium. So we find for this assumption, also under assuming 1,000 open channels and 1,000 seconds, we get during that time here a very strong equilibrium of 100 to 1,000 fold of the total cell calcium content. So this is a very strong calcium overload of the cell, which should be cytotoxic for many cells. So this can explain that radiofrequency alone is already cytotoxic, which we have seen and published in this publication recently in scientific reports. But now we come to the second model. We have to understand why amplitude modulation can enhance the effect. Then we assume that the periodic force of amplitude modulation should be mechanically transmitted, look at the circle here, to the surrounding membrane, stimulating self-resonances. And you see the modulation frequency is superposed to the DC voltage here, and it can be transmitted from the ion channel to the surrounding membrane. This is our assumption and our model. And so what we have to, and modulation frequencies has been found to be specific for certain tumors. This was a result of the application, the preclinical studies, and also clinical observations for the Terabionic device. Membranes consist of vibratory sections that resonate with eigenfrequencies f depending on the stiffness. This is a Young module and the size A and B. You see this is the size of the section A and B, and the section is here fixed to some transmembrane proteins. And the physical background, so if we look for theory of elasticity, this is a physical background, we can calculate the resonant frequency of such a section. And this eigenfrequency or resonant frequency depends on the stiffness, or also called Young module, and of course of the dimension of the section. So this is the formula, and we have to look if this is realistic and can describe our data. Eigen oscillations of the membrane can be stimulated by numerous channels and might cause rupture as an extreme. So this is shown here. If the membrane is resonating in the eigenfrequency, which is induced by the channels, it can increase, it can form a hole. But this is, of course, an extreme. Prior to rupture, shear stress might cause membrane depolarization and, as a result, opening of channels. So if there is a depolarization, especially for the T-type calcium channels, small depolarizations will already open the gate, and then a strong calcium inflow is possible. And I should also mention that there are dipole sensors in these ion voltage-gated channels, which might be sensitive to various kinds of electromagnetic fields. And there is an interesting review about many other studies which describe calcium imbalances by Paul, 2013 already published. Coefficients of elasticity of cell membranes had been investigated by biophysicists. And we know that this is a book, an interesting book, Mechanics of the Cell, which has all these theoretical and this physical background is described in this book. We have two elasticity parameters which describe the membrane. The first one is a volume compression modulus, which is nearly a constant for every membrane, which represents the incompressibility of a fluid. But the second, which is much more interesting and relevant, is a Young modulus or stiffness. And this can vary from cell to cell in the range of 100 to 10,000. These are two decades Pascal in various cell lines, and this represents the fluidity of the membrane. So resonant frequency F decrease with decreasing Young modulus and increasing extension A and B, if the vibrating membrane section is larger. So, but one example, this is a minimal frequency we can obtain, is for Young modulus of 100 Pascal and A and B of 10 micrometer, then we get an eigenfrequency of 24 Hertz. And this is probably the minimal eigenfrequency we can get with that theoretical approach. If we look in the literature, then we have interesting, there are already measurements of the Young module in several cell lines. And we see already that the normal cell here in the lung has mostly higher stiffness of larger than 1000 Pascal, but the tumor cells have decreased Young modules or stiffnesses in the range of several hundred Pascal. So you see this has been shown for breast, here normal, nearly 2000, and for the malignant cells, several hundred only, and ovary is the same. The normal cell has more than 2,000, and the malignant cells has less than 1,000. Malignancy is associated with larger membrane fluidity that enables better infiltration and metastatic potential. And now you see that we expect for tumor cells lower eigenfrequencies, which are in the range of hertz to kilohertz. So you see that if you use this formula I have shown to you, then you get eigenfrequencies of malignant cells in the range of kilohertz. So you and hertz. So you understand?
Yeah, sorry, yeah, but
that there might be an eigenfrequency. So I come to the conclusion. Now I'm ready. Summary. Radiofrequency alone causes fluxes of ion channels, especially for voltage-gated calcium channels. Additional amplitude modulation adds effectiveness. Specific modulation frequencies in the range hertz to 10 kilohertz exist for tumor cells, causing eigen oscillations and elevation of intracellular calcium. And tumor-specific frequencies depend on the channel lomes, also from the oncochannels, and elastic behavior of membranes, and knowledge and consideration of tumor-specific channel lomes and elasticities might improve therapeutic ratios. Thank you very much for your attention.
Okay, thank you, Professor Gust. Very interesting. We don't have questions in the chat box, so maybe I think your presentation is really interesting. It's complex also, so maybe if you can write your address email, someone may write you with some questions, and that way we can go on with the meeting because we are like 15 minutes late. Okay, so thank you. So let's